Welcome. Today I'm doing a problem set created by Dr. Aaron Wiegand of the University of the Sunshine Coast in calculus. And so let's begin here with part 1, question A, where we're asked to find the mean value of y equals x over the interval from 0 to 10. Okay, so let's have a look at the formula above. Mean value y bar is 1 over b minus a times the integral from a to b of f of x, but f of x here is just x, and a is 0 and b is 10. So then we have the integral from 0 to 10 of x with respect to x, and we multiply it by 1 over 10 minus 0. Okay, so now we need to integrate x, and we have 1/10 a half x squared from 0 to 10. Okay, so now what we do is we take the 10, we sub in, we take the 0, we sub in, and we subtract those two. So we still have 1/10, 1/2, 10 squared minus a half, 0 squared. And then we just simplify these fractions and simplify the whole lot. Okay, so bringing the 1/2 out, we have 1 over 20 times 100. And this is 5, isn't it? So the mean value is 5. And so let's also draw a picture so you can understand what this means. So here we've got the line y equals x, 0, and then let's call this 10 here. Okay, so the mean value is the average value of the height of this function. And so the height of the endpoint there is 10. The height of the middle is 5, and that's actually the average value of all of these heights. Okay, let's do problem B. So it's similar to this. So we'll have the same A and the same B. But our function now is y equals x squared. Okay, so let's use our formula. Y bar is 1 over 10 minus 0, integral from 0 to 10 of x squared with respect to x. And so we have 1/10. Integrating the x squared, we get 1/3 x to the power of 3 from 0 to 10. Now we need to sub in those values. So let's pull our 1/3 out of this first. So we have 1 over 30. 10 to the power of 3 is 1,000. 0 cubed is 0. And so now we can cancel the 10 that's in both of these. So we have 100 over 3. And so we can approximate this or write a decimal expansion of it. And so this is equal to 33.3 recurring. Okay, so similarly, let's draw a little picture of this. So y equals x squared looks something like this. And then if we take this to 10, then what do we have here? We have 100. Okay, so the claim here is that the average height is 1/3 of that, so 33.3 is the average height. All right. Let's move on to the next one. So in part C, we've got to do the same thing with the function y equals x cubed over the same interval from 0 to 10. Okay, and so let's use our formula. Y bar is 1 over 10 minus 0, integral from 0 to 10 of x cubed with respect to x. And so we have 1/10. The integral of x cubed is a quarter x to the power of 4. Okay, now we sub in our numbers. So let's write 1/4 times 1/10. And then we have inside 10 to the power of 4 is 10,000. Okay, and so now, canceling a common 10 in there, we have a quarter of 1,000. And a quarter of 1,000 is 250. So the average height of the function y equals x cubed is 250 over the interval from 0 to 10. All right, now let's do part D. So we've got y equals sine of x, and our interval this time is the interval from 0 to pi on 2 radians. So using the formula, y bar is 1 over pi on 2 minus 0, integral from 0 to pi on 2, sine of x. Okay, so we integrate sine of x, and the integral of sine of x is minus cos of x. And out the front, we have 1 on pi on 2. Let's put a bracket around this so it's clear what we mean. Okay, now simplifying, we have, pull the minus out the front so this is less confusing. Now the multiplicative inverse of pi on 2 is 2 on pi, so we'll have minus 2 on pi. And then in brackets, cos of pi on 2 minus cos of 0. Okay, now pi on 2 is 90 degrees. So the way I think about this is I draw myself a little triangle whose angle down here, a right triangle that is, whose angle gets close to 90 degrees. Okay, and I'm thinking about adjacent on hypotenuse. Well, this is getting close to 0, so that reminds me that cos of pi on 2 is 0. Minus 2 on pi, and so we have 0. Now cos of 0 is 1. Okay, and so we do get 2 on pi as our mean value for that interval. Okay, next we have in part E, y equals sine of x again, but this time the interval is different. The interval is from 0 to pi. So how does that change things? Well, the mean value now is 1 over pi minus 0, integral from 0 to pi of sine of x dx. And so we have 1 on pi, again, minus cos of x is our integral, but this time from 0 to pi rather than 0 to pi on 2. So let's bring our minus out. So minus 1 on pi, and then we have cos of pi minus cos of 0. Okay, now cos of pi, isn't that minus 1? So if we go all the way across to here, with our triangle adjacent on hypotenuse, that should be -1. Minus another 1, and so that gives us 2 on pi. Okay, part 2. So here we have delta A, meaning a change in area, is equal to 2 pi times x, and so this part is the circumference, times delta x. Okay, so what I am describing here is what you see here on the left. We are estimating the area of a circle, or calculating the area of a circle, using the sum of the area of these annuluses that you see with a dashed blue line there on the left of my screen, and those areas are in orange. All right, so the area of the annulus, and I'll do my best to draw the picture of one of these using my coffee cup here. Okay, and then we want to do the inside of this. So here is one annulus, and so the circumference is 2 pi x, so this part of it, and that's all the way around here. So let's just put a dashed line, and then multiplying this times the width of this annulus, which is delta x. So delta x is this width across here. So now if I cut this, here are my scissors, and I stretch this thing out, then I have a rectangle where the height is delta x and the width of this is 2 pi times x, or the circumference around here. So the area of this is that circumference, 2 pi x, multiplied by delta x. And so here what I need to do to get the area from, say, here to out here, I need to add up the sum of all those rectangles to get the area. And so what this would be is area is equal to the integral from 0 to the radius of 2 pi x dx. Okay, so we need to calculate this. And so this is the integral 2 pi x. So we have 2 pi times a half x squared. As x goes from 0 to r. Okay, so in the circle that I have on the left, we've got x between 0 and the radius of that circle. Okay, so finishing off the calculation, so we've integrated, and now we need to sub in the r, sub in the 0, simplify, so 2 divided by a half is 1, so we have pi x squared, but then we sub in r, so pi r squared minus pi times 0 squared, and so we get that the area of the circle is pi r squared. Okay, part 3, we're calculating the area bounded by two functions. So in part A of part 3, we have the function y equals x squared minus 6, and we have y equals x. So the first thing we need to know is where the two of these functions intersect. So that's when the two y values are equal. So x squared minus 6 is equal to x. And so we need to solve x squared minus x minus 6 equals 0. Now you can see that this clearly factorizes as x plus 2 times x minus 3 And so the points of intersection are x equal -2 or x equal to 3. And so the area bounded there, shown on the left, is the integral from -2 to 3 of the difference of these two functions, but we have to get the top function in front, and the top is y equals x. So x minus, in brackets, x squared minus 6 dx. Okay, so here's our integral, and now we just need to calculate this. So we have the integral from -2 to 3 of x minus x squared plus 6 with respect to x. And so this one is a half x squared minus a third x cubed plus 6x between -2 and 3. Okay, great. So now we need to sub in the 3 and sub in the 2. So we have 3 squared is 9, so 9 over 2. 3 cubed is 27. 27 over 3 is 9, so minus 9. 6 times 3 is 18. And then we subtract, big bracket for this, subbing in -2. -2 squared is 4. 4 over 2 is 2. Okay, -2 cubed is -8. -8 over -3 is 8/3. So plus 8/3 there. And then 6 times -2 is -12. Right, so simplifying these, 18 minus 9 is 9. So we have 9 plus 9 over 2. And then over here inside the bracket, we have -10, but then there's another minus, so that's a plus 10. And then -8 over 3. Okay, so this is 19 plus the sum of those two fractions, which is a difference. But we want to write that 19 over 6. So 19 times 6 is 60 plus 54, which is, and I'll just write 60 plus 54, and then we'll put that over 6. And then we want to write the two of these over 6. So 9 times 3 is 27, and then -8 times 2, that's 16. That's over 6. All right, so we are nearly there. So 60 plus 54 is 114. And then over here we have another 27 minus 16 is 11. And that's all over 6. Okay, so we get 125 over 6 as the area between those two functions. But let's get Mathematica to check this. And I'll just press integrate. So 125 over 6, and that looks good to me. Okay, moving on to part B of part 3. So in part B, we are asked to calculate the area between two sine functions. Okay, so that's shown there in orange. So y equals sine of x, and y equals sine of x plus 3, the 3 outside the bracket, and our interval is x is going from 0 to 7. Okay, so the area we want, now we take the taller one, subtract the smaller one, so sine of x plus 3 minus sine of x, integrating with respect to x as x goes from 0 to 7. Okay, so simplifying this, the sine of x will cancel. We just have the integral of 3 with respect to x. So 3x, now that's x going from 0 to 7. And so we have 3 times 7 is 21 minus 0. And so we get 21 for that one. All right, next. Okay, part C. So in part C, we have y equals sine of x and y equals cos of x. And we are integrating between 0 and 1.5. Okay, so first, where do these two curves intersect? So where do we have sine of x equal to cos of x? Well, think about this triangle with sides 1, 1 and root 2, the right triangle that is. So the angle in here is pi on 4 radians when we have equal side lengths. And so the sine of pi on 4 is equal to 1 on root 2, and that's the same as cos of pi on 4. Okay, so the answer is when x is equal to pi on 4. Okay, so this means then that we need to break up our interval and say that the area is the integral from 0 to pi on 4 of the difference between these two functions, where if I don't want to put in an absolute value, I need to think about which one starts out being above, and so that would be cos. So cos of x minus sine of x. And then we add to that, now we swap the order of these because they cross over at this point, pi on 4. We want to add up positive areas, pi on 4 up to 1.5. And this time, after that intersection, sine becomes the higher one. And so we need to calculate the sum of these two integrals. All right, and so the integral of cos is sine. The integral of sine is minus cos. So minus minus cos is plus cos of x. And the integral of sine is minus cos. And the integral of cos is sine. Whoops, not dx, because I've integrated now. So pi on 4 to 1.5. All right, now let me just double check this. The derivative of cos is minus sine, so the derivative of minus cos is plus sine. Okay, great. And so now we sub in our numbers, subtract, and we'll get the area that we want. Okay, so sine of pi on 4 plus cos of pi on 4, but both of those are 1 on root 2 based on that triangle. Okay, let's bring out the minus. So we'll have minus in brackets. Oh no, we've got to do this first. So that's plus sine, no, it's minus sine of 0 minus cos of 0. Okay, now for this one, we bring out the minus. And so we have cos of 1.5 plus sine of 1.5. And then we subtract cos of pi on 4. And we subtract sine of pi on 4. Okay, now we need to simplify these, add them all up, and get a number. So sine of pi on 4 plus cos of pi on 4. So this is 1 on root 2 plus 1 on root 2, but over here again we have a plus 1 on root 2 and another plus 1 on root 2. So that is 4 of the 1 on root 2, so 4 on root 2. Okay, now sine of 0 is 0, cos of 0 is 1, so we have a minus 1 from this. And then we have minus cos of 1.5 minus sine of 1.5. All right, and so now I should go on to the computer and calculate this -1, and then we have a +4 on the square root of 2. Okay, that looks right to me. So we have 0.7602 approximately as our area bounded between those two functions in that region. We are asked to find the area between the curves y equals cos of x and y equals x, but we'll need to look for an intersection. Okay, so let's display this. Now, this is between x is 0 and x is pi on 2, which is about 1.57 or so. But you can see that there is an intersection between there. So this is somewhat problematic because this integral will start subtracting from itself as these cross over each other. And so we need to break this up. So y equals cos of x and y equals x. Now you might wonder, okay, well, we need to know where the two of these intersect. So they intersect when the two y values are equal. So intersection occurs when x is equal to cos of x in radians. And so let's let f of x be equal to x minus cos of x. And we're seeking a root of this, or a 0 of that function. Okay, so where does that occur? Now, you can't solve this algebraically too easily. So what we'll do is we'll seek a solution numerically. And so Newton's method is one way to do this. And so Newton's method would say, you take a guess of, say, x0 equals something near it, say 1.0, and then a sequence of better approximations to a root of this would then be, so we'll say Newton's method is our approach here. And so xn plus 1 equals, what is it if I remember this right? Xn minus f of xn over the derivative f dash of xn. So this is what I want to calculate with x0 is 1.0. Okay, so this is Newton's method. Let's do this with Mathematica. So I've just tabulated, making a list of these values. Okay, and so these seem to be converging. Let's say converges with root 0.739, and I'll just chop it off at 3 decimal places, approximately. Okay. Now let's just double check this. If I take this number, take its cosine, let's see what we get for that. Okay, so we get a number very close to that number itself. So this looks reasonable to me. Okay, and so now let's have a look at our picture. So our area bounded between the two of these, we've got to take a sum. So it's from 0 to alpha, where alpha is this number. Now the taller one in that case is cos of x minus x dx. And then we need to add to it the integral from alpha up to, where do we stop here in the question? It's pi on 2. And incidentally, this alpha that we found is less than pi on 2. Okay, and so now the taller one after that is x. So x minus cos of x. Okay, so now we can just calculate. So let's integrate cos, we get sine. Integrating x, we have a half x squared. This is from 0 to alpha. And then we're adding to that this definite integral. So a half x squared minus sine of x from alpha to pi on 2. Okay, now let's simplify. So we have sine of alpha minus a half alpha squared, and then minus sine of 0 minus a half 0 squared. We'll just put 0 for that. And then this part, we have plus a half pi on 2 squared minus sine of pi on 2. And then we subtract from that a half alpha squared minus sine of alpha. Okay, now this part of it here is just 0. So let's simplify a little bit. So minus minus, so we have plus sine alpha there, but we have another one here, so that's 2 sine alpha. And then we have 2 of these, so minus alpha squared. And then we have plus pi squared on 8. And then minus sine of pi on 2. Okay, so let's simplify this using the computer. Let's just take this number here, and I'll call that A. You can call it alpha if you like. It's just easier for me to write A here on the machine. And then I want 2 sine of A minus A squared, then plus pi squared on 8. And then I want to subtract sine of pi on 2. Okay, so I get approximately 1.0346. But let's call it 0.47 if we round this to 4 decimal places there. All right, let's move on to part E. Of part A. And so I need a plot for this. Let's have a look. Okay, so now we're seeking the area bound between the y-axis and y equals the square root of x. Now that's given there in the hint. And so we can write this in 2 ways. So we can say that this is the integral from x equals 0 to x equals 9, because remember the square root of 9 is 3. Okay. Of 3 minus the square root of x. Right, so that's the difference between the 2 functions. And then we need to integrate this with respect to x. Okay, so integrating, we have 3x. Now the integral of x to the power of a half, I'm adding 1 to the exponent, so I have x to the power of 3 halves, and then dividing by the new exponent, that would put a 2/3 in front. So this is from 0 to 9. Okay, and so now let's sub in the 9. So 3 times 9 is 27. And then the square root of 9 is 3. So this here would be 3 to the power of 3, which is 27. 27 over 3 is 9. So this is minus 2 times 9. And then we subtract 0 and 0. So this then is 27 minus 18, which is 9. Okay, now we can do this in another way as well. We can express this as an integral from 0 to 3. That's y equals 0 to y equals 3 of y squared with respect to y. Okay, and this is possibly an easier version of the same thing. So integrating y squared with respect to y, we have 1/3 y cubed from 0 to 3. And so this is 1/3 of 3 cubed is 27. And then minus 1/3 of 0 cubed. And so 27 over 3 is 9. 9 minus 0 is 9. So again, we have 9. Okay, part 4. Volume of rotation or volume of revolution. In this case, we're revolving a function around the x-axis. Okay, so part A of part 4, we have y equals the square root of x over the interval from 0 to 2. And so let's draw a quick by hand sketch of the function. It looks like this, but then what we're doing is we'll spin this around the x-axis, and so we get something like a bowl shape. Now the radius of a slice of this will be the square root of x, and then we'll use this formula. So we have pi r squared, and then we need to sum those up. So this formula is appropriate for that. All right, so let me show you this in Mathematica 2, and then we'll get started calculating. All right, so this is what this looks like. If you shift it this way, you have the side view or the projection being the function y equals the square root of x, but then that gets rotated about the x-axis, and so we get this sort of bowl shape. And we want to calculate the volume of this. Okay, so let's use our formula here. So v equals the integral from 0 to 2 of the square root of x squared with respect to x. So we're integrating x with respect to x from 0 to 2. So integrating this, we get a half x squared. And we need to sub in the 0 and the 2 and take a difference. Okay, so 1/2 of 2 squared minus 1/2 of 0 squared. That's 4 over 2, which is 2. Okay, next one. Let's have a look at part B of part 4. So in part B, we have the function y equals x cubed, and the interval this time is x between 1 and 2. And so if we plot this function, y equals x cubed, remember it has an inflection point at the point 0, 0, and then it curves up and goes almost exponential. Okay, so if we take this and rotate it around the x-axis, then we get this end down here, and then we have a bowl-shaped volume like that. Okay, so let's plot this one as well using Mathematica. All right, so there we go. Now that's between 1 and 2, so at some point here at 1, we're starting the calculation, so we're calculating the volume of this. All right, now v is equal to the integral from 1 to 2 of x cubed. Hang on, I have forgotten the pi in this calculation up here. So that puts a pi there, puts a pi there, a pi there. And so we'll get 2 pi for that one. Okay, good. And so we don't want to forget the pi in this one. And that gets squared. All right, so simplifying this, we have pi times the integral from 1 to 2 of x to the power of 6 dx. So integrating x to the 6th gives us x to the power of 7 over 7. And so we simplify this, subbing in the 2 and the 1 and subtracting. Let's pull this 1/7 out. So 2 to the power of 7 minus 1 to the power of 7 is 1. Okay, and I'll just keep that volume like this. All right, let's move on and do part C. And let's have a look at this function. So we have y equals sine of x, where x is between 0 and pi on 2. So if we plot a sine wave, it comes up like this, and it peaks out at pi on 2. Okay, so if we take this and revolve this around the x-axis, then we have this bowl shape, and that's what we've plotted here. Okay, so calculating the volume of this, v is equal to pi times the integral from 0 to pi on 2 of sine squared of x with respect to x. All right, now we've got some hints for how to do this integral. So we can write sine squared of x as 1 minus cos squared. Okay, and now, since we have cos of, let's put 2t equal to 2 cos squared t minus 1. Now, what I want to do is replace the cos squared using this identity here. So let's do some algebraic rearrangement. So add 1 to both sides and then divide by 2, and we have cos squared of t is 1/2 of, in brackets, 1 plus cos of 2t. Okay, and so here we can replace this here. And so do this integral by substitution. Minus. Then we have, if we expand this, we have 1/2 and then another minus 1/2 cos of 2x with respect to x. Okay, so 1 minus 1/2 is 1/2. And then we have minus 1/2 cos of 2x integrated with respect to x. And so let's put a big bracket around this. Okay, so now we need to integrate this, but it's much easier than looking at that and wondering how to integrate it. So now we've made some progress. Okay, so let's integrate the 1/2 first. And so what I'm doing when I do this is I'm breaking this integral up like this, and then we'll subtract pi on 2, integral from 0 to pi on 2 of cos of 2x with respect to x. Okay, now you can do this in your head, or you can set out a u substitution letting u equals 2x. So I'll do this in my head. But let's go over here and finish this off first. So we have pi on 2, the integral of 1 with respect to x is x. So then we will have pi on 2 minus 0 for that part. Okay, then we come over here. We have minus pi on 2 times this integral. Now the integral of cos of 2x with respect to x is something times sine of 2x. Now if I differentiated sine of 2x, I would generate 2 there. So we need to compensate for this and make it true by putting a 1/2 there. So now if we differentiate 1/2 sine of 2x, we will get, using the chain rule, cos of 2x. Okay, so let's finish this off. So over here we have pi on 4. And then we have minus pi on 2 times 1/2 sine of pi, subbing in the pi on 2, and then minus 1/2 sine of 0, subbing in the 0. Okay, so sine of pi should be 0. Sine of 0 is 0. And this is a minus there, so we should get pi on 4. All right, so now I'm going to double check this with Mathematica. Oh, sorry, pi on 4, right? Okay, let's double check. Pi, integrate sine of x, and then we square that, integrating this with respect to x from 0 to pi on 2. And we get pi squared on 4. Okay, I see. I've forgotten the square here because the pi, 2 pi's, so there's a pi squared. Yes.